So we're going to start today with the question I posed yesterday, which I see a lot of people looked at, but maybe no one was willing to dip their toe in on. I asked about whether it's possible a function could be its own derivative, and the easy one doesn't count. The easy one, by the way, if you're not sure what I'm talking about, would be f of x equals 0. Then you take the derivative of f, and it also is 0 because it's a flat line with no slope centered at the value 0, right? So that was a straightforward one, but some of these questions are really worth thinking about. You know, could it change signs is a fascinating question. Imagine what happens when a regular derivative, or a regular function, right? Let's just use the pen here for a sec. When a regular function changes signs, right? In order for a function to change signs, it has to either decrease through the axis, right? Or it has to increase through the axis. But what's happening to the function at this moment is it's changing signs from negative to positive, but its derivative has to stay positive, right, in order for the function to keep going through the x-axis. So you can try to think like, well, how would a function ever get through the x-axis if it had to have the same value as its derivative, right? It would have to, so let's say we drew a function that was, positive and increasing. Something like that could technically be its own derivative because, look over here, the slope is small and positive, and then over here the slope is a little bit bigger, and the function is a little bit more positive, and then a little bit bigger and a little more positive, and so on. Something like this is possible, maybe, to continue on. But if this ever, actually goes through the x-axis, you can't do that, right? You can't draw a function that goes through the x-axis and expect it to be its own derivative. So all I'm asking you to do here, if you maybe were thinking about this and not sure what to say, just consider some of these questions and show me, would it be able to do this or not, right? Just to give a quick example of one that looks kind of close, if you take the function 1 over x squared, right, and then let's look at its derivative. Obviously the right side is no good because the red function is very high and positive, but its slope is very high and negative. So the right side of this is no good. So let's say we were doing function f from negative 1,000 to 0 only, and then we took this derivative, right? So you can kind of see like these are not bad matches for one another, right? The function and its derivative look really close together, except as you know, a polynomial, even a rational, with a negative exponent, the exponent's always going to drop down by 1, right? So it goes from 1 over x, so x to the negative 2, and then it drops to x to the negative 3. And you're never going to be able to get those two to line up perfectly well. Now that being said, if you look at, if we continue this concept and draw, an exponential function, look at what an exponential function does. Its slope is small and positive, and its value is small and positive, and then its slope and its value both get a little bit more positive, and then a little bit more positive, and then they kind of rapidly get more positive, right? Now, I don't know I doubt it will figure this out, but yeah, I can draw a curve, but of course it doesn't draw a curve the way I want it to. But anyway, I'll just test that. So let's take an exponential. So let's say 2 to the power of x. Now look at the values and look at the slopes of this function. Over here, the value is very low, the slope is very low. Over here, the value is a little bit higher, the slope is a bit higher. Over here, the slope is higher, the value is higher, and so on. Let's trace the derivative. Okay, so remember, how do we trace the derivative? We take the slope of the tangent to f at point A. Suppose it would help if I spelled it right. Okay, the slope of the tangent here is 13.14. Let's draw another function that has the same x value as a, but as a y value, it has that slope. Okay, and let's trace it. Now observe what the derivative of this function looks like. Right? It's not a perfect match, but it is a perfect match in terms of the shape, which is an important idea, that the derivative of an exponential function is another exponential function. We're not used to that, right? Because usually we do the derivative of a quadratic as a linear, and the derivative of a cubic as a quadratic, and so on. But the derivative of an exponential is another exponential. Let's take the derivative of f, and you can see it sort of has this new thing, this ln2, but let's just leave that to the side for the second. But you can see that it is in fact another derivative. Now, or another exponential. Now let's say we wanted to change the base of this exponential, because I want to show you something here. If we draw 3 to the x, and then we take its derivative, I want you to notice something about the two derivatives. In the original case, with the case of 2 to the x and its derivative, so let's get rid of 3 for a second. Do you notice that 2 to the x is above its own derivative, whereas 3 to the x is actually below its derivative, right? 3 to the x comes out below its derivative. That must mean, right, that there is a function somewhere in between 2 and 3 where it's going to line up perfectly with its derivative. Okay, and let's demonstrate that right now by changing this function from 2 to the x to b to the x, and we'll get rid of the 3 here. Now, you can see as I change the base here, they look really close, and then it's like green is above red, and now red is above green, right? So there must be some value in between those two where we can get them to line up really closely. And in fact, if you notice here, at this number 2.7, right, it's really close. Let's try and get it a little more close. Okay, so again, let's zoom in quite a bit so we can try to line them up. Okay, so you can see they're really, really close together here. Maybe would help if I actually compress, no, stretch that out. Okay, so you can see, like, again, they're really close together. They're just slightly off at 2.7. So let's try to shift it a little closer. And here you can see they line up almost perfectly, around this number 2.718. Now on your calculator, you probably have a button that looks like this, e to the x, right? E to the x. E to the x is a particular logarithm with a particular base. And if you do e to the power of 1 on your calculator, it's going to give you this number, 2.718, and it continues on. It's an irrational number. It's very similar to pi, right? It's a mathematical constant that has an important meaning, but the number itself is a non-terminating decimal. And for us, where we are first introduced to this number e is in the concept of a derivative, where this particular function, so let's take this this number e to the power of x, right? And then take its derivative of h, and its derivative is just itself again. And this is where you're going to meet this number, and sort of like, this is the property about it that you want to know, that if your base is higher than e, then your derivative is going to be higher than your original function. If your base is lower than e, then your derivative is going to be lower than your original function. But if your base is e itself, right, then your derivative is exactly the same function as the original. And so this is a really interesting result, and why e to the x is such an important value. because its derivative is itself, and therefore it is very easy, or it is easier, to take the derivative of a function when you use the base of e. Okay, so it says in this section we're going to study e to the x and its derivative. The number e is a special number, it's very similar to pi. It's an irrational number that has some important properties that we can use. The number is called the natural number due to its many associations with phenomena in nature. I don't want to get too much into that, but if you're interested, there's lots of things to read about how e is relevant to natural phenomena. It's named after this man named Euler. Again, it's a Swiss, so it's not pronounced the way you might think. Pronounced Euler. And, it's about 2.718. So, to graph e and its derivative, we just did. So, if you can fill in this table if you like. We can go ahead and do that. So, let's just take, let's make a new, and we'll just get some numbers here. So, e to the x is going to be our function, and we'll go f of negative 2. It gives us 0.14. F of negative 1 gives us 0.37. F of 0, of course, gives us 1. F of 1 gives us e, which is equal to 2.718. Sorry, I'm not sure why this. There we go. 2.718. This one would be e squared, so f of 1 gives us 2.718. F of 2 gives us 7.39. Okay, now the derivative, if you were to take the tangent in each of these places and do the difference quotient, which is, I think, basically this is asking you to use a graphing calculator. We're not going to use the TI-84 graphing calculator, but we can use GeoGebra. So we'll go derivative f. It creates f prime, but f prime is just the same function. And f prime of negative 2, f prime of negative 1, f prime of 0, f prime of, sorry, it would help if I actually wrote f prime. F prime of 0 and f prime of 1 and f prime of 2, they are all the exact same numbers. Right? This is 0.14, 0.37, 1, 2.718, and 7.39. Right? So this is a unique function. Its derivative is itself, and no other exponential function has that property. Right? What conclusion can you make about the function e to the x and its derivative? For the function f of x equals e to the x, we're going to write this really important property. We would if my equation editor would open, but I'm going to pause this and get that fixed. One sec. Okay, so for the function e to the x, it has this really important property: f prime of x equals f of x. Okay, that is to say, f prime is also equal to e to the power of x. Okay, so this is a unique function, really important to us in the exponential functions unit, where the function is its own derivative. Okay. Now, with this number as a base, you have an exponential function e of x, which has a unique property, and again, that property is the one we just wrote: f prime of x equals f of x. Right. So that would be what you could say there. Now, e to the x has an inverse, right? Remember, an inverse, what does an inverse do? It undoes whatever the original function did. So let's say we're going back to GeoGebra for a sec, and let's say we wanted to check let's say f of x is e to the x, and I want to know f of 3. Okay, is that 20.09? Now, how do I get from 20.09 back to 3? Okay, you have another button on your calculator called ln, and it should be beside log or close to log. ln, and ln is the natural logarithm, it's called. Many people just sort of pronounce it as ln. It's not really supposed to be pronounced as ln. I probably will, because no one told me this when I learned it the first time, and it just stuck with me. But you're supposed to say natural logarithm, right? So The natural logarithm, if I take the natural logarithm of 20.09, I get my 3 back. Okay? So whatever you do with e, you can undo with the natural logarithm button. Okay? And that's just what this section here is just going to quickly show. Well, let me go back to it. Okay? So the inverse is a logarithm, but it's a particular logarithm. It has a particular base. And rather than write log base e like that, we just write ln, right? So natural logarithm. So if we say log base e of x, that's the same thing as what people say ln, or natural logarithm of x. Okay? So the logarithmic function, again, x is equal to log base e of y, right? Oh, sorry. Right? So that's how you rewrite it. Remember, you write the same thing in logarithmic form versus exponential form. Okay? Oh, I'm sorry, I misunderstood. I see what they're going for here. So let me just write this down over here. To create an inverse, swap the location of x and y, then isolate y, right? That's what we're doing here in order to make an inverse. So I see what they're doing. Just misunderstood that. Okay, so first thing we're going to do is swap x and y. So we put the y up there in the top, and we put the x over here. Now, to isolate y here, you need to, so let's just review another thing. To change exponential form to logarithmic form, use this template. Okay, so basically what we used to have is power equals base to exponent, right? That's what exponential form looks like. Logarithmic form is log of the base, the power equals the exponent. So this statement up here and this statement down here are the exact same thing. They mean the same thing. So for example, in the first one, 4 equals 2, let's not use that, sorry. Let's use 8 equals 2 to the power of 3, right? That would be an example of the first statement. Written another way, you could say log base 2 of 8, same mistake I made before, equals 3, okay? And that is, these two statements are equivalent. They're just a different way of writing the same information. So what we're going to do now is we're going to apply that idea here. The exponent is isolated if the other side is the log with the base of the power. Now, of course, log base e, we want a shorter way of writing that as opposed to writing log base e all the time. So we just write ln, right? And this is the inverse of the original exponential function. Okay, so let me just make a new page here. Okay, so all the normal properties of exponentials and log also apply to these two. So let's just quickly draw what this looks like, and you can see. Let's make a new one. Okay, so let's draw the function f of x equals e to the power of x, and then let's draw the inverse g of x equals ln x, right? And you can see they have a type of symmetry. They have a special type of symmetry called they're reflected across the line y equals x. So for example, if I plot a point on the logarithm function, the exact same point will exist straight across the line over here, right? And we can do that by saying reflect the point A across the line H. And what happens there is that point is always going to be exactly, of course it gets a bit tricky here because but the point is still there, right? I don't know if I can kind of move it like this, but right? So it's always directly across from it. It's always a perfect inverse. Remember, the other way to recognize an inverse, look at the coordinates. The x coordinate of A is the y coordinate of A prime. And the y coordinate of A is the x coordinate of A prime. The x and y's have swapped, okay? All right. Now, so if you want to draw that one right here, you can draw it, by the way. How would we draw it? Notice it has a vertical asymptote at x equals 0. it always passes through the point 1, 0, and then it rises very, very, very slowly. It does rise forever, but it rises very slowly, going off in that other direction. So, you could draw something that has an asymptote here, passes through that 1, 0, and then kind of rises off the page up and to the right. Okay. So let's look at some properties. Remember, the domain of the exponential is the range of the logarithm, because the x and y's switch. The range of the exponential is the domain for the logarithm. Okay, and again, that's just a consequence of inverses where the y and x switch locations. The y-intercept of the original swaps to become the x-intercept of the new function. Right, so maybe we can do that in green actually. Okay, so the intercepts of course track, because every point on the original, if you swap the x and the y, will be a point on the original. A horizontal asymptote on the original, becomes a vertical asymptote on the new one, and of course the y becomes an x as usual. Now, the one thing where you do have to be a bit careful here is, if you notice, if I draw f of g of x, it produces something. If I draw g of f of x, it produces something a little bit different. This is an important question that I asked if you had me in advanced functions, but if you didn't, then this, I want you to think about why these two are different. If I say e to the power of natural logarithm of x, it produces the line y equals x, right? So it produces a straight line with a slope of 1, but only positive. If I do it the other way around, where I do the e to the x first and then take the log, I get the full line. So I'm going to post this question to the website. I want to know, if these are inverses, how come these two things are not equal, right? So I'm going to put this one here. So of course this is equal to, they're both equal to x, but one has a restriction and one does not. So I'm going to post this one to the front page of the website. Again, just take a shot at it. You don't have to be right. You just have to get your idea out there, right? Why are the final two statements not the same? Why does one have a restriction? Okay. Down here it's just asking us to do some practice, and then we're going to take some derivatives, and that'll be it for today. So let's do this right here where we're evaluating. It says the natural logarithm of e to the power of 3. Well, the natural logarithm says, what power would I need to raise e to in order to get, and then the second part of the question is e cubed. Well, the answer is obvious. I would need to raise it to the power of 3. So the answer is 3, right? And all that they're trying to show you here is that natural logarithm and e cancel, and all you're left with is the 3. Now, to be careful with this one is true all the time. The other one is not true all the time. So, and we're going to get to that point when we get to C. Now here, 4 times the natural logarithm of e plus 3. All right, so let's just, sorry, I found these questions a little easier to do if I make them vertical. So that was my answer for A. Okay, for B, it's asking, what is 4 times the natural logarithm of e plus 3? Well, remember, the natural logarithm of e is equal to 1, right? Because you're asking, what power would I need to raise e to in order to get e? And the answer is I would need to raise it to the power of 1. If you're not convinced of that, actually type it in, and you'll get 1, right? So this one is, it's just a trick question. All that's asking is just 4 times 1 plus 3, and that, of course, is equal to 7. Now, this is a trick question as well. C. I'm going to make an error here. I'm going to say the answer is -1, which is wrong. I want you to explain why. Why is -1... oh, wait. No, I'm not reading the question properly. Sorry, I ignore what I just said. Okay, sorry. So e to the power of minus 1, and then you take the natural logarithm of that, gives you the minus 1. So let's just, sorry, threw you off there. Okay. That's what we have, right? Let's just concentrate on the top part. So concentrating on the top part, you should see that the top part all simplifies to simply -1, right? E to the power of -1 is e to the power of -1. When you take the natural logarithm of e to the -1, you just get the -1. Now I still have an e here at the bottom, so I raise, I just do e to the power of -1. And that is a number, we did it earlier, I think it was 0.37, right? So I'm just going to write equals approximately equal to 0.37. Okay? Sorry, I mixed that one up with something else. For this one, e to the power of the natural logarithm of 5, well, again, just use your rule from above. E to the power of ln x just gives you the x back. So e to the power of ln 5 just gives you the 5, and you get 3 times 5. Okay, you just get 15. Again, these ones are really good to try. Okay, they'll help you remember your exponent rules, and just help you practice with those. So redo those ones or do the ones in the book until you get comfortable with them. If you have a question, please post it. I can try to explain it again if I didn't do the best job the first time. Now, when you are taking the derivative of e, it's easy. I mean, as long as you remember a couple of things. You remember the chain rule, right? The derivative of the chain rule, right, is that f of g of x, right, has the following derivative. F prime of g of x untouched, and then g prime. That's what the chain rule said. So let's just do the chain rule with what you see here. My f function is e to the x. My g function is 7x, right? What's going on in this question? I'm taking g and I'm subbing it into f, right? I'm taking 7x and plugging it into e. So what do I get here? The derivative says I'm supposed to do f prime. So let's write them out quickly. F prime is e to the x, and of course g prime is simply 7. So let's put all the parts together. I'm supposed to do f prime, which is e to the power of something. Then I'm supposed to repeat g of x exactly as it was the first time, and then I'm supposed to multiply all of that by the derivative of g, which is the 7. So your final answer here is 7 times e to the power of 7x. Okay? Again, these ones are always easily checkable. Just pop on GeoGebra, go derivative r, and there you go, right? You just double check any of your derivatives doing that pretty easily. Okay? I don't want you to think that the 7 comes down in front. Try to think of it as a chain rule. The derivative of the top comes down to the front. Okay? You can think of it that way if you want. Okay? So here it is in general. It says if you take e to the power of a function, you copy it out again exactly as it is, e to the power of a function, and then you take the derivative of the function. Okay? So this will some of these examples will help clarify this, I think. Okay? First one. It says e to the power of x squared. So the derivative is f prime is equal to e to the power of x squared. Okay? Don't touch it. And then take the derivative of the exponent. The derivative of the exponent is 2x. So there's your derivative, right? Again, let's just double check. Let's just go back here. E to the power of x squared, and then I go derivative f, and I get 2x times e to the power of x squared, right? Exactly what we said we should get. Okay? This next one, this is a good challenging one here. This is a product rule. That's a product and a chain, really. Okay, let's remember how to do a product rule. F of x is x squared. That means f prime of x is 2x. G of x is e to the power of negative x. And that makes g prime. Let's remember, how do I do the derivative here? Copy it out exactly as it looks, and then take the derivative of the exponent. Sorry, -1. We can simplify that again. We can say negative e to the power of negative x. Okay, that's what our derivative of g looks like. Now the product rule, if you remember, if we say h of x is f times g, then the derivative is f times g prime plus f prime times g, right? You have to do all four of those parts. So now we're just going to do that. We're going to put all the parts together. So our derivative here is I write f first, that's x squared. Then I write g prime. That's negative, let's just put it in a bracket so it doesn't look like subtraction. Negative e to the negative x. Then I say plus, f prime is 2x, and then I have e to the power of negative x. Now I want you to notice something about this. Okay, really important idea here. Since e to the x is its own derivative, you will always be able to common factor it at the end of your differentiation. Now this is hugely important because, right? Why is this important? Because if you want to solve this, which we often do, right? There's no way I spelled that many words wrong. I mean, it changed my language to French. Okay, well. You know, it never ceases to amaze me what must be a hotkey for that, right? Maybe an extra bonus communication point for whoever can tell me what that hotkey was. I'm kidding. Anyway, you look at this one. Let's just clean this up a little bit. H prime of x. So let's take the negative to the front. So you have negative x squared e to the power of negative x, and then we have plus 2x e to the power of negative x. Now again, if you're trying to solve this, you should remember from advanced functions that solving with powers that are being added is a dead end. You can't add powers easily. Instead, what you want to do is you want to factor. So look, both of them have an x, both of them have an e to the negative x, right? Let's see what's left when I do that. There would be a negative x left of the first term, and there'd be a 2 left of the second term. Now look at this and tell me how easy this is to now find the minimums and maximums on the original question. We know that there's going to be a critical point when x is 0. There's going to be a critical point when x is 2. Okay, now again, this is not what we're doing today. I just want you to think ahead. Right? We're not solving anything today. That actually was a mistake. We're not actually solving anything today, but if you were to solve something, you could see how this would be really, really helpful. The fact that factoring, they're always going to both have an e to the x because we know it's its own derivative, so we're always going to be able to pull that out, and then we can solve. Let's just draw this one quickly. I know this is off topic, but just while we're at it, because I do want you to be thinking about where we're going with this stuff. Okay, so there's the function we were asked to draw. Kind of like on the one side it goes off to infinity, on the other side it kind of has like a bump and then a horizontal asymptote. And look where those critical points are. There's a critical point at 0, right? So if we go min between min of f between negative 2 and 2, we get that critical point. And then if we go, what's the max of f between 0 and 10, we get the other critical point, right? And you can see where those two came from. One of them came from this factor, and one of them came from that factor. Now, of course, the e to the x factor itself is never equal to 0, right? So it's never going to give you an answer in terms of like finding a critical point. I do highly recommend when you're doing these derivative questions in today's practice, factor the final step. Okay, get used to doing that because you're always going to have to do that in any of the actual problems that we do. Okay, this next one is very, very straightforward. It looks difficult, but it really isn't. Y prime here is e to the x minus 0, right? Because, of course, e to the e is a constant. There's no variable there. Remember, e is not a variable. It's a value. So the derivative of this function is simply e to the x, right? I like that question. It's very simple, but you do need to know your stuff in order to answer it. So y prime here is simply e to the x. Okay, last question. It says y is equal to 5e to the negative 2x. What would y prime be? Okay, the 5 is still there because it's a coefficient. E to the negative 2x is still there because we know that when you take the derivative of e, nothing changes. Then you take the derivative of the top, and that's what you get. So your y prime in this case is negative 10e to the negative 2x, and that's what you should be getting for an answer there. Again, let's check it. 5 times e to the negative 2x, then we'll take its derivative of g, and we get negative 10 e to the negative 2x, right? Exactly what we said we should get. Okay, determine the equation of the tangent to the line y equals x minus e to the x at x equals 0. Okay, now I'm going to do 2. I'm going to leave you 3 and 4. I'm going to open up a discussion question. I want one of you to do this. Okay, more of you ideally, but at least check the work of the person who did it, right? And go through and make sure you got it the same. If you're really struggling, obviously I'll help you, but I think this should be within your realm of being able to do at this point. I will do the tangent question just to remind you. What do we need to get a tangent? We need f prime of 0 is equal to our slope. We know that f of 0 is a point on the tangent. Let's also remind ourselves that a tangent is going to be given by y equals mx plus b. That's what a tangent is. You're looking for a straight line that has two qualities. Its slope is the same as your function slope, and its point is the same as your function's point. Okay, so let's find the point first. Okay, so we know that our function f of x is x minus e to the negative x. Okay, so the point on this equation, f of 0, therefore, is equal to 0 subtract e to the power of negative 0. Now, of course, negative 0 is the same thing as 0, and f of 0 is therefore equal to 0 minus 1, and f of 0 is equal to negative 1. Okay, so let's draw this one so we can see it. So x minus e to the negative x. Okay, I'm saying that this function should go through the point 0 and minus 1, which you can see that it does. Okay, so there it is. Goes through 0, minus 1. Okay, so we know the point we're interested in is 0, negative 1. What I need to know the slope, and then I can plug in this point into my y equals mx plus b, and I'll know the tangent. So now let's work on the slope. The slope we know is equal to f prime at the point we're interested in. So let's find f prime. Let's write the function one more time. X minus e to the negative x. Take the derivative, f prime of x. Okay, the derivative of x is 1. The derivative of e to the negative x is e to the negative x times negative 1. So our derivative here is 1 plus e to the negative x. Okay, that should be our derivative. Again, get in the habit, might as well just check it. Derivative f, okay, 1 plus e to the negative x, exactly what we said it should be. Let's find the slope of, so let's find f prime at 0. What's f prime at 0? Plug it in. 1 plus e to the power of negative 0, which is f prime of 0 is 1 plus 1. Remember, anything to the power of 0 is always 1. Okay, so therefore our slope is equal to 2. So now all we need to do, we need the equation of a line with a slope m equals 2 that passes through 0, negative 1. Well, this is especially easy because if you remember, mx in y equals mx plus b, b is equal to the y-intercept. So in our case, b is equal to negative 1. You can see that it has to have that y-intercept. Let's say we didn't recognize that. We would sub in our y value. Negative 1 equals m, which is 2, times x plus b, right? So let's just write, I'll just write this quickly. Y equals mx plus b. Plus b. Okay, and then negative 1 equals 0 plus b, and therefore b is equal to negative 1. Therefore, the tangent that we're interested in is y equals 2x minus 1. Okay, let's draw that function. Y equals 2x minus 1. And you can see that that is a perfect tangent for the point we were interested in, right? Okay, so I'm going to leave the other two with you. This one is find all the points where the tangent is horizontal. This will be a very good test of, did you understand the point I was making up here about factoring and solving it? So again, you should be able to do that. If you're really struggling with that one, check the discussion forum, see if anyone else has done it that you can follow. If if a day or so goes by and nobody does it, you can ask me and I can help you with it. Show me what you tried or how you got started, and I can take it from there. This one, again, the challenge here is taking the derivative. So try to take the derivative. You don't really need to do any factoring here, although you might challenge yourself to try. You want to find g prime of 1. All you're looking for is the value of the derivative at a specific number, so you can do that. Okay, so I'm going to leave those two. I'll make a discussion forum for each of them, and I also am going to post on the very front of the website, which I'm just hoping for a little discussion or short answer. Why is one of these restricted and one of them not restricted? Okay. Lastly, if there is anyone who wants to weigh in on the function being its own derivative on any of these other points, I'd be interested to see what you have to say here. I think this is the kind of test your brain for thinking and stuff. So if you're asking me questions like, how do I do better? How do I prepare better? How do I, I'm trying to give you these opportunities, right? To think this out and try, this could be a really good thinking question on a test, right? Is it possible that this function could exist? And, I tried to break it down for you. Could these different things happen? You should be able to go through each of these and say, is it possible I could draw a function that has a turning point, for example, and its derivative has a turning point in the same place, right? Make an argument to me if that's possible or not. Okay, anyway, you got a lot to do here, so go over this, see what you think, and again, reach out if you need any help.